Today we're going to be doing a little bit of work, which means we're going to be taking our knowledge of how to use integration to answer questions, applying it to physics, specifically problems involving work and force. Now the same ideas are still present. In other words, take the quantity that we're looking for, we're going to break it into little tiny parts, add all the little tiny parts together, and that will be what we're after. Of course, it's going to be in a slightly different setting, but that's all right. It just needs a little bit of work. All right, so let's get going. So what is work? So work is force times distance. In other words, I have some object that's being moved, and I move it. So boom, it's been moved. So what we do is we take the force associated with that object. Usually we think of it like a number of pounds, and we say, okay, how far was it moved? We multiply those two quantities together. So it's very easy to compute if you're in a very simple setting. Namely, your object is constant weight, and you move it. But what if our object isn't a constant weight? Something's happening to it. Maybe it's leaking, or as we're in the process of moving, things get thrown in and it gets heavier. So now what do we do? Well, so when things vary, we say, look, let's break things into small parts. So what's our basic idea? It says, well, if I'm moving something from A to B, and here's my object, and at any time x, I'm thinking x as a location right now, there's some force attached to it. What we can do is we say, instead of thinking of it all in one big movement, let's think of breaking things up into little tiny parts. And so, why little tiny parts? Well, so now we're going to think about, well, we're going to move it a little bit, and then a little bit, and then a little bit. And so, and then we're going to add up all these little movements. But what's the advantage here? Well, the advantage is when we talk about moving just a little tiny bit, the force involved becomes essentially constant. Now, why do we like things which are essentially constant? This is what we would have called, when we're doing our geometry, flat. So basically it says, look, now that you can treat it like it's a constant, because it doesn't going to change much. It's going to be more or less the same. Now you just apply the old formula. It's whatever the force is times the small amount of change. And then that's the amount of work to move that little distance. So in particular, I say, look, the force at that location times the distance, that little part, so the delta xi, that's the little piece right here. This is our delta xi. The subscript I is just saying the ith one, because we're breaking up into lots of little ones. So here, we say, look, here's the little piece of work in the ith step. Add them all together. Now, of course, the idea of integration says, well, chop things into smaller and smaller and smaller pieces, and then our sum becomes an integral, because integration is all about adding things up. Integral from start to stop, A to B, the force times the distance. And here, we should emphasize, you see, dx is not just a notational convenience, it represents something. In this particular case, we see that the dx is attached to saying, I'm thinking of that as being the little distance I move at every single step. Now, depending on the problem, that might change. So make sure you understand what's happening, what does dx represent. Now we can look at this and say, okay, how about the units? Does it make sense? Well, if we think about what's going on here, we really have two pieces. We have the force, so that's the units of F, and we have the distance. See, that dx represents the distance, so that's where we get the units of our distance. And so we say, aha, if our force is being measured in pounds, distance in feet, we get foot-pounds. So there we go. So that's the idea of work. Break things into little tiny parts, add them all together, and there you go. Now, one interesting case that might show up, something called Hooke's law. Now, Hooke's law is actually not about work, it's about force. And it says the following. Imagine that you have a spring. So there's a spring, and you have something attached. Well, it does this, but what will happen is you can imagine that you have the spring, and if you attach some weight, it stretches the spring. And so now, well, the question becomes, well, how much does it stretch? So that's where force comes into play. So we say the force that will compress or stretch a spring past its natural length. So you can think of this line right here as the natural length, or you might think of it as the sort of resting state. Nothing has been acted upon. You attach a force to the bottom, it stretches it. So the question becomes, well, how much does it stretch? And the answer is that there's this beautiful relationship that the force that you've attached is proportional to how much it stretches. So in other words, you attach a heavier object, it'll stretch it further. You attach a lighter object, it'll stretch it less. So how do we use this? Well, now you can say, suppose I take a spring. I take my spring and I start pulling it, stretching it longer and longer and longer. Well, how much work am I going to do? Well, you have to be a little bit careful here, because what happens is the force varies. You see, initially, it's not too hard to stretch the spring because it's near its resting state. It doesn't take very much work. But the longer you pull it, the more the spring resists, the more it's saying, no, I want to come back to my natural state. So it takes more force. So what does this become? Well, it says, if I want to find the work to stretch a spring, I say start wherever it currently is at. So we think of it in terms of relationship to its resting state. So remember, when we talk about x is how far it is from its natural resting state. So say we start from its resting state up to some marked distance b, and then we say the force at any stage, because the force is varying, then a small distance, force, distance, and then we can figure it out. Of course, we have to know k in order to do it, so oftentimes there's k's given, or we can find it through some other method. All right, well, let's do another variation. This one is a very popular variation. This is about pumping from a tank. So what do you have? Well, you have some container. So here's a container, and here it's an upside down cone, and it can be any shape, doesn't really matter. But inside of it is material. And what we want to do is we want to take the material that's inside the container and move it out. And so there has to be some work involved to do that. And the question is, well, how much work does it take? We know the basic philosophy. Work is force times distance. So what we need to do is figure out, okay, what's my force? What's my distance? And so now we get to one really important question. And it's actually so important that we have to pause for a second and say, notice something that often is not given. If I show you a picture like this, one of the things that we don't put in there are coordinates. So when you're doing a problem and you start talking about various measurements, the first step, step one, is to choose good coordinates. Now you'll notice I added the word good. Not just choose coordinates, but choose good ones. Now, they might have a coordinate system already handed to you, in which case, probably you should use it. There's a reason they handed it to you that way. But if they didn't, then we have to make a decision. So, how do you decide? The answer is put coordinates in a way that makes it easy to work the problem. So, for instance, here, you might say, well, let's put 0 at the very bottom. And now I'll relate things to where 0 is. There is actually sort of two things you should do. One is figure out where 0 is. The other thing is which direction is positive. Now, that seems like you can't really have a choice, right? Because isn't positive always up? And the answer is no. That's just a convention. You just make it whatever you want. So 0, we can say make positive this way. All right, so I want to put some coordinates in place so I can talk about things like distance. Because when I talk about distance, I want to have some sort of measurement. And I don't just want to say, well, it's this-ish kind of thing going on. Okay, our idea here, our goal, let's move things out of the tank. And in particular, we want to say we move them up to some certain height h. So the goal is we're going to move them up here. So I'm going to think of this height, y equals h. That's where I'm shooting for. Now, what to do? Well, here's what we do. We're going to think about, instead of moving all the material at once, we're going to break our material up into little pieces. And we're going to do it in a smart way. So, how do we break our material up? You can actually see we've highlighted it here. We're going to break it up so that there's just a very thin slice at a particular depth. And y here. So let's say this right now is our current y value. Well, what do we want? We want to be able to make sure that when we break things up, they're more or less constant. Now, constant with respect to what? Well, what we want to do is just make sure that the measurements that come into play, we can treat them like as if that whole slice were behaving the same way. And there's two important measurements when we talk about work. There's the force, there's also the distance. When we slice this way, then we say, hey, we're okay to go, because we can look at our coordinate system and say our distance is essentially a constant. And what constant is it? Well, in this case, it would be h minus y. It depends, of course, on your coordinate system. You have to be careful. But if we choose to slice this way, our distance is no problem, because we have it, essentially it's the same for the whole slice. On the other hand, if we were feeling somewhat crazy and we said, well, what if we slice this other way? Mwahaha, couldn't we slice this way as well, where we take a slice in a sort of a different direction? Well, you could slice this way, but this is a bad slice. Now, why is it a bad slice? Well, notice what's happening with your height. Your height is going to vary quite substantially over your slice. So you can't treat height like a constant, and therefore integration is not going to work. Because in order to do integration, our little pieces, our important measurements have to be like a constant. So this is why we slice in these things which are perpendicular to the vertical direction. Okay, so that's the answer to the question you weren't asking, but it's good to understand why things are done the way that they're done, so that we understand how to adapt to various situations. All right, so where are we at? So we have our slice. Let's return to our regularly scheduled slice. So we have our slice here, and now what we're going to do is we're going to say, let's take our slice and let's move it up and out. Well, so we have a distance. That part, now, that's straightforward, easy. It's going to be something like h minus y. No problem. Life is good. We need the force. Okay, so now we say, well, let's think about our force. Well, what we have is there's some sort of material, and it has a density attached. So when we think about density, we can think about it as like pounds per cubic foot, as an example, is our density. So, since we have some sort of density in play here, we say, all right, well, what we'll do is we'll take our density times the volume of the slice. Well, the density is whatever the density is, And we know how to find volume of slices. It's the same sort of philosophy that we talked about when we figured out volumes of these shapes. We take the area of the cross-section times the height. So the height there. So area times height gives a volume. Of course, it's not exactly right. It's an approximation. But again, the error is very small. That's why we break things into small pieces. The approximation to volume is very good. The approximation to height over the whole thing is very good. And therefore, we say, look, the work for one slice, we can get a good approximation. It's a distance, a density, an area, and a little thickness. So this part becomes our volume on the end. Now, of course, we say, look, do integration. So we integrate from C to D. In terms of the picture, when we talk about C and D, C would be where the shape starts, and D would be where it ends. So it might be you have a container, it's not completely full. You only go to where the material that's being moved is going to end. That's where your bounds are. Not the container, but where the material is. So C and D is where the material starts and stops that you're going to move out. You have our distance, density, area, thickness. Notice something. When we did our force integral before, we had, integral of f of x dx. Our dx represented, that's the little distance that we're moving things. Now, the distance that we're moving things shows up there. Here, this has a different meaning. This is being used to help compute the force part. And so, keep in mind that what the little d thing represents will vary depending upon what application we're doing and how things are being set up. That's why it's not just there for show, it's there for a very specific reason, and it's doing a purpose. And so once you understand how everything gets set up, it's easy to understand how things fit together. By the way, let's look through the units and make sure it makes sense. So work should be foot-pounds. So distance will usually have some measurement of feet. Density, well, that's going to be pounds per cubic feet. Area, well, that's a square feet, and this distance here is simply feet. And if you work through your units, you'll see that you have a cubic feet over cubic feet, so that this last part is indeed a force, it's pounds, and then times feet. So we end up with something foot pounds. Exactly what we should have if we're talking about work. All right, well, one more idea. So the other thing that we might want to do is called fluid force. Well, what is this? You can imagine here there's a picture of something like a dam. And you have this liquid, again, just think of it like water, pushing against the dam. Now, one of the things you'll notice about dams is that if you look at a cross-section of them, they tend to be a lot thicker at the bottom and a lot thinner at the top. Why is that? Well, what's happening is that if you look at the water, it's pushing against the dam, and it pushes against the dam at all levels, but it actually pushes more, in some sense, at the bottom. Now, why is that? Well, here's how you should think of it. Is the water, it's trying to get out. So the way this happens is you can imagine you put a very tall, thin weight on top of the water. And so there's this column above the water. And now you have this water here being compressed by what's on top. Now, what happens is the water, it wants to shoot out. And it's just like, phew. Of course, it's being prevented because something is holding it back. Now, what if you were to compare a very tall piece to a very short piece? Well, what would happen is that the tall piece, there's a lot more pushing down, and therefore, when you have the water here, it's much more likely to be like, "Ugh, ugh, ugh." There's a lot more pushing out, trying to get out. Whereas here, it's like, oh, there's not too much on top of me. I don't feel too much stress to get out. So what's happening? Well, this is actually what's happening all the time. You see, wherever you have water, there's always the water above it. So the further down you go, the more pressure you get, because all the water above you is pushing down on you, and you're trying to escape out in any direction, including a horizontal direction. And that's why, if you ever go diving, if you go down further and further and further, you start getting more and more pressure on you because all that water is pushing in on you from above you as well. So, what do we have? Well, we have that our force at a constant depth is we have to take into account our density of our material and our depth. And that's what's pushing down. So that's pushing down on us. And then we have the area. So the area, what does this correspond to? The area is the picture. This is our area. It's our little tiny piece it is pushing against. Okay. So how do we proceed? Well, now we have a plan. So we have our various shape. It could be submerged in the water somewhere. So here's our shape. And we say, look, if I want to understand what's the force acting on this, what we do is we say, well, let's break our force up into little tiny parts. So we start stripping it. In other words, cutting it into very small, tiny, thin strips. And we say, hey, we can figure out what's happening for any single part. That's our generic formula. So what do we have? Well, we have our density. So that's our little omega here. So density. Then we have our depth. And now we have to do our area. Well, how do we do area? Well, what we do is area is a length and height. So our length, that's how far across we are. So our length, you can also call it width if you prefer. And our dy, that's our how far up and down we go, that's our height. And so we see, these little pieces correspond to what makes up the force of that very thin strip at a certain depth. And of course, we add them all together, and that gives us our total force. So that's the idea. Break things into small parts, figure out what's happening with each part, add everything up, and life is good. It's the same principles as before. Nothing has really changed. But now we get to do things with physics. So, as they say, we're going to get to use the force. And of course, we should probably practice that. So let's go do some practice.